Okay, good morning to everybody. We are going to start with the seminar. Okay, our speaker today is Guillem Anglada. I am sure that all of you know Guillem for many years. But in any case, let me tell you some words about his career very quickly. He presented his PhD in the University of Barcelona some years ago. A few years ago, in fact. Okay, and although he performed a big part of his work for this doctoral work in Mexico already at that time, after finishing his PhD, he got a postdoc grant from the Generalitat de Catalunya, and he has been visiting very often both UNAM in Mexico, and also he's a frequent collaborator. In fact, he was for a sabbatical there also at the Center for Astrophysics in Boston, in USA, where he has collaborators with who he has been working during all these years. As you know, he's now investigador científico of the CSIC, and he got a permanent position here many years ago already. But also I want to mention that he got a position in Mexico as Profesor Titular B, if I'm not wrong, and he was Investigador B. He was there for a year before coming to the Institute. He has been also Vice Director of the Institute for 4 years, together with José Carlos del Toro, and he was even Director for a short time, and he has been also always very active in the scientific life, and also in the let's call between quotation marks in the political life of the Institute. I always said when I have something that is not clear about the CSIC, the IAA, the laws or administration, I always ask Guillem, because I am sure I'm going to get the right answer to it. Okay, but essentially and I am sure about it, he's a reference in the scientific field in which he has been working during all these years. You know, he has been mainly working in the physics of the interstellar medium in many different aspects, and especially let's say in the observations with very high angular resolution of the processes of star formation, making I would say key studies of the formation of the individual stars of the jets that are associated with these processes of star formation, etc. Okay, and I think he's also very open to many collaborations, and I think that there are a number of people here in this room that has cooperated with Guillem in different papers. But today he is going to tell us about a very recent work that was published, I think, at the end of November of last year in the Astrofísica journal, and it's about the study of the architecture of the planetary system around Proxima Centauri. As I have just mentioned in my briefing before, I think this is a nice project because it has implied the collaboration of many scientists of the Institute, those involved in star physics, those involved in the study of the dust, of the dust belts around the main star, those that are also involved in the study of the planetary system around Proxima Centauri. And okay, this is a result of the work of many people that have been involved in that, as Guillem will tell us. And I think it provides a very nice result. And I think what is still more important, it will provide in the near future still more interesting results. Okay, Guillem, when you want, go ahead.
and have some apportations to what can be done from different point of view. And these are just the first results. In this work have participated many people, many of them from the IAA and also from other international institutions. The basic idea was to better understand which is the architecture of the possible planetary system around Proxima Centauri, which is the closest star to the Sun, in addition to the radial velocity studies that are being carried out, and it was because of these kind of studies that the discovery of the planet was made. There are also other studies of photometry of the star, searching for possible transits. And we took a different approximation. We tried to understand the system from the point of view of the radio observations. It was known that the star, or at least the proximity of the star, there was radio emission, but it was non-thermal radio emission. And there is an ongoing project to study this non-thermal radio emission, and I hope that soon we will have a presentation of these results also that look very, very, very promising. These results have been carried out at the Australian compact array, the ATCA interferometer, and the observations were carried out by José Luis Gómez and José Francisco Gómez, and the data are reduced and they look very, very interesting. What I will present are the results carried out in the millimeter wavelength range with the ALMA observatory. These kind of observations can reveal belts of dust, clouds around the star, and if we know about these rings or belts of dust, we can infer the inclination of the system, because a phase-on system will look very circular, and if the inclination increases, then the system will look more elliptical. And so we can infer from the ratio of the major and minor axis the inclination of the system with respect to us. And this is very important to derive, as we will see, the true mass of the planet discovered around the system. This was one of the main goals of our approach. This can also provide information about the dynamical history of the system, because if we find belts of dust, we can infer the possible position of the planets that have resulted in these belts, possible resonances, and look for other possible planets, and also other kind of features. I will present the Proxima Centauri system. It is the closest star to the Sun. It is in fact a component of a triple system, the Alpha Centauri system, which is composed of two stars which are with a mass similar to our Sun. One is a bit more massive, and another a bit less massive, and then a star much less massive than our Sun, that at this moment is the closest star to our Sun. But we know that the orbital period of the Proxima Centauri star is about 500,000 years. So in several thousand of years, it will not be the closest star to the Sun, but currently it is the closest one. This is less massive, it is an M star, and this is the kind of targets that are very useful to search for Earth-like planets. for example, with the Carmenets project. It's interesting that the confirmation that this it is a triple system which is gravitationally bound was obtained just a few months ago in the summer of 2017. I was surprised about this result. I thought that the closest star to our sun was much better characterized. So Proxima Centauri is this M-dwarf star. It belongs to a hierarchical triple system, and in this system what happens is that after many orbits, a smaller mass component is ejected, and the two other components, they get closer. So they become a very close binary system, so the period of this system is much shorter. I think it's about 100 years or so. And this one that has been ejected to an orbit with a much larger semi-major axis has a much longer period. So this is Proxima Centauri. This is colder than our sun at 3000 K. The radius is about 1/10 of the solar radius, and the luminosity is a very small fraction. So the age is similar to that of our sun, and so we will expect that everything is much more smaller than in our solar system, because the temperature, the luminosity, and everything is much smaller. So in fact, the planet that has been discovered is only at 0.05 astronomical units, so much closer than the Earth to the Sun. But at this distance, the temperature is similar to the temperature that can be at 1 AU in our solar system. So this is why it is said that it is in the possible zone of habitability of this star. The mass that had been estimated from the detection is 1.3 times the Earth mass, but this is multiplied by the sinus of the inclination angle. So we need to know the inclination to know the true mass. So the mass will be much more bigger if the inclination was higher. So the determination of this inclination is an important factor. So the discovery was made was led by a person with the same name as me, and this is not me. And one of the motivation for me to undertake this project was to participate in a paper when people could see that we were two, not just one, Guillem Anglada. And well, we reached this goal partially. So the process started with the call of Pedro Amado to me when I was on vacation in 2016 in August in Menorca, and he called me and told me, is there any way to detect with ALMA to make an image of the planet Proxima b? So I made a back of the envelope calculation, and if you have a sphere and you consider it as a black body, which is the most efficient way we can have, and you assimilate and you think this sphere has the radius of the Earth, and you put this at a distance of 1.3 parsecs, the distance of Proxima Centauri, and you assume a temperature of 300 K, which is 27 centigrade, so it's a reasonable temperature. In fact, it's the temperature that is reported in the paper. And the maximum flux density that we can expect at millimeter wavelengths, 200 gigahertz is 1 millimeter, more or less, is given by the area. This is more complex because it depends on the phase of the planet with respect to the star, which will illuminate only a fraction, and also the radio emission comes from the the underground and is delayed with the phase, but the maximum value you can obtain is this value, which is the radiation of upper body. It's 0.05 micro-Janskys. In radio astronomy, we use Jansky as the unit of measure. The strong calibrators have like 10 Janskys or so. So this is 0.05 micro-Jansky. So just as a reference, in 2.5 hours with ALMA, the noise is 10 micro-Jansky, which is much more bigger than this, so it's clearly undetectable. We'll need about 1 million hours of time in ALMA to detect this at 5 sigma, okay? Because the detectability goes as the square of the signal to noise. The time that you need to increase the signal to noise. However, if you have the same mass, but in this way you will smash the planet and you make it very small pieces, then you increase a lot the surface. And the number of the particles will go as the ratio of the volume, so it's the ratio of the radius to the cube power. So you have that the emission that the same amount of mass, but in dust particles, will increase as the ratio of the radius of the planet and the radius of the particle. This is why, because if you have the planet, you will only see the surface, but if you break this, you will see all the pieces that are inside. So the surface increases a lot. And what matters is the surface, in fact. So in this case, of the smashed Earth, or the smashed Proxima B, if, for example, we break it into particles of 1 millimeter in size, and we will have that the flux density will be 600 Jansky. If we assume that we do not have the planet with 300 K, but a ring much colder, like, for example, a Kuiper belt, which is about 30 K, then will be 10 times smaller, but we will have a very, very strong source. So what matters is not the amount of mass, but mainly the amount of surface you have. And so then in one of our discussions, then José Luis Ortiz suggested, is it possible to detect an analog to a Kuiper belt in Proxima? So my answer was, well, maybe. Okay? Maybe because even when the mass of the Kuiper belt probably will be much less than the mass of the planet, in fact, the Kuiper belt in the solar system is about 1/100th of the mass of the Earth, the possibility of detecting this is higher in principle. So we start to make some calculations and some estimates to see if this was feasible. In the case of the solar system, there are effectively belts of dust, like the Kuiper belt, which is outside from Neptune, and even the inner belt, which is the asteroid belt, which is between Mars and Jupiter. And also in the orbit of Jupiter, there are two clouds that are called the Trojans, and that precede and go about 60 degrees before and after the position of Jupiter. So there is possible to detect dust, in principle, in other stars, because in our solar system there is evidence that this dust is present. There is also the zodiacal dust, etc. However, dust is associated to the process of star formation, and this is one of the fields in which I have been working for many years, because the stars are formed from the collapse of big clouds of dust and gas. In this process, the material concentrates towards the center and makes the star, and at the same time, this gas and dust is distributed around the star, forming a disk, and then finally this disk will form the planetary systems. Just to have an idea, if this is time 0, this is about 100,000 years. This is about 1 million years when the planet formation starts, and the formation is considered finished more or less about 10 million years after that. In this process, the gas is removed from the planetary disk, and finally they only remain the bodies. In these phases, there is a lot of gas and dust, but progressively this amount of dust and gas also decreases. So as the system is more evolved, there is less amount of dust and becomes more difficult to detect it. So here is very powerful, but when we start in this phase, in the phase when the planet formation starts, which is about 1 million years or so, the amount of dust is smaller than at the beginning, but still is very significant. This process is now pretty well studied, in particular after the ALMA observations, and what are called transitional disks are considered the beginning, the onset of the planet formation process. It's the disks appear cavities and gaps, angular gaps, that are supposed to be produced by the presence of planets. It is not very well understood yet, but in principle tidal effects of the planets create these gaps and dust. Then the gas is removed probably because of photoevaporation by the UV radiation and X-rays of the star. And for example, here we found evidence of this process of the gas being photoevaporated. So this is an example of a star of 5 million years. This is about when a star of similar age, between 1 and 10 million years, but here this process has started of photoevaporation. I calculated the flux density of these stars if they were at the distance of Proxima Centauri, 1.3 parsecs. So this will have 10 to the 4 Janskis of flux density. This one will have 10 to the 3 Janskis. But when we go to stars which are in a phase similar to our Sun, about 5 gigayears, this will be 100 millijanskis, this one 16 millijansky, 24 millijansky. So we found that the stars which are similar to our Sun, there are very few of them that have been detected, actually, a millimeter wavelength is dust, but these are almost all the examples that we can find where they were imaged and we can characterize them. And we see that these two have a mass similar to our Sun, and the flux density is of the same order, and this one is more similar to Proxima Centauri, 0.2 solar masses, and well, it is 10 times smaller than this. If we look at this in somewhat more detail, there is an additional factor that can be relevant. In the case of our solar system, there is the known NICE model that José Luis Ortiz has explained it here a couple of times. And it occurred that when the solar system was about 0.5 gigayears old, there was a resonance between Jupiter and Saturn, and because of that, they were reversed in their orbits, and the initial Kuiper belt that was very much more massive than currently was dispersed. And in this process, the two planets were reversing their orbits, and all this material was dispersed and becomes 100 times less massive than currently. And these pieces of the initial Kuiper belt were dispersed in the system, and this is what is called the late heavy bombardment of the planets. Okay, so in our solar system, if we were observed the system at this age, just before 0.5 gigahertz, we will have seen something 100 times more stronger than currently. So we do not know if our solar system is an exception or it is the rule. So we can think that, for example, this object, when we see this nice disk with 100 or 200 millijansky, maybe is younger than this one, and for example, in this one, the flux density has decreased by a factor of 10. So if we want to make an estimate for Proxima, because Proxima has a mass similar to this guy of here, we in principle will expect a flux density of about 20 millijanskys. But we do not know if this guy had suffered something similar to our solar system. So our expectations were that the flux density of a possible Kuiper belt in Proxima Centauri will have a flux density between 0.3 and 30 millijansky, the factor of 100 of uncertainty, because we do not know if this process has occurred or not. Another thing that we need is the size. So to do that, because everything in Proxima is much smaller, we will expect that the analog of the Kuiper belt will be much closer to the star for two reasons. Because if we want to reach a temperature similar to the temperature in the solar system Kuiper belt, which is about 30 Kelvin, we will need to go of about a few AUs from the star. Also, if we look at the density of the solar system, what is called the minimum mass solar nebula, which is constructed by adding the gas to the density of the planets, and we extrapolate this to Proxima, which is extrapolation with 1 point, because only there is one planet, but Jose Luis Ortiz did it. So he reached the bright conclusion that the radius of the analog in Proxima will be about 5 AU. So we proposed to detect this belt. If the belt was the size of our Kuiper belt, it was very difficult to detect with ALMA, because ALMA is thinking to look at very small things. So if we try to look at something very big, it's very difficult, because we will see only a small fraction. So we had to demonstrate that this should be very small. So they do not believe us completely, so they say that we have to do some tests with a small array. ALMA is composed of 2 arrays. It is the main array with about currently, it should be more than 50 antennas of 12 meters in diameter, but now there are 41. And this is the compact array, also called as ACA, the Atacama Compact Array, which is made of antennas smaller, 10-meter antennas, and just 10 antennas. So this one array can see bigger things easily. The problem is that it's much smaller and it is 10 times less sensitive. So they told us, if you want to observe with the main array, first you have to demonstrate us that this is detectable, but using this array which is 10 times less sensitive. Well, it was pretty difficult, but we found some evidence at least to convince they to give us the full time we requested. And I will show you the results. The results of the ACA array, the smaller array, which has a poorer angular resolution. The beam is 6 arcseconds in size, which correspond to 8 AU, shows this image. So we see here a source. The cross is the position of the star obtained from an optical plate obtained by José Luis Ortiz and his team at the same date, so it's clearly. And one of the problems is that this star has a very large proper motion, so just in a couple of months it moves for more than 1 arcsecond, so it's difficult to track, so we wanted to be sure that this was really the star. So this appears as an unresolved source with this angular resolution. So this means that the emission comes from a region with a radius smaller than 4 astronomical units. However, they tell us, why are you sure that this is not simply the emission of the star? Because we wanted to see the dust around. So we making a simple calculation of a black body at 3000 K, I obtained 90 microjanskis for the star, because the flux density was more than 3 times higher. We have some evidence that this is not just the emission of the star. A more detailed model published by Ignacio Ribas results in a flux density of 74 microjanskis. It is a model, it is extrapolation, but also is in agreement. So there is evidence that this is not just the emission of the star. Okay? So we can say, in principle, within the uncertainties, that we have detected dust emission around the star Proxima Centauri. So what do we see with the ALMA? I will show you an image of ALMA, which is bigger, but I will show you just this portion, which corresponds to what the size of the beam of the ACA. So this is what ALMA sees. And ALMA sees a point-like source at the center with a flux density of 100 microjansky. So we think that the star, we expect 74, so it is in agreement. So it shows us that these 360 microjansky come from a bigger region, because at the position of the star should have a size of 1 milliarsecond, much more smaller than the beam. From this, there are only 100 microjanskis, which is in agreement with the emission, with the expected emission of the star. This source is not completely point-like. This is the beam, and in this direction, this size is bigger. So there is the possibility that here, the total flux is 106 microjanskis. There is about 30 microjanskis or so that can come from dust very close to the star. There is also here another source, I will tell later, with a flux density of 40 microjanskis. This can be just a noise peak, or can be something very relevant, we do not know currently. And where is the remaining 200 microjanskis? Well, the remaining flux density is spread over all this region. What happens is that when you go to a higher angular resolution, you make your beam smaller, and your beam catch less photons than if you have a very big. So here, these 200 microjanskis are spread over many beams, and the sensitivity per beam is not enough to detect any of them. Increasing the observing time, it should appear, if we are correct, some flux density additional spread over here. Okay? So this tells us also that these 200 microjanskis are spread in a region smaller than 4 AU in radius, because it appears unresolved in the previous observation, but should not be very small, because if it was compact, they should be detected here as a stronger source. So it should be at intermediate distance between this and this. So we estimated that it comes somewhere from 1 and 4 astronomical units. So this is very disappointing because we know that there is dust because we do not see the dust in the higher resolution observations. But this is what we had, what we can do with the DBT time that we got. It was some exploratory, of course, observations. Another interesting thing is that Mayra realized that this source appear aligned, and this can be maybe a bigger ring, an outer ring, which has not an analog in the solar system, because this is about 30 AU in size, which will be the same size that our Kuiper belt. To confirm that, there is one trick, which is make the average emission averaging over elliptical rings. And when you average the emission over a ring, it's like if you average the emission, you will have a different position. It's like if you integrate more time, so the signal-to-noise ratio increases as the square root of the length of these ellipses in units of the beam. So, making this, we found that in these average rings, there is a peak at 24 arcseconds, which correspond to 30 AUs. And this is the central peak, and this is the secondary peak, which coincides with the ring. This appears for a precise combination of ellipticity and orient position angle. So if you make, for example, circular rings, this vanishes. If you make with another orientation. So there is some evidence that there is an outer ring of 30 AU in radius, which will be much colder than the analog to our Kuiper belt. If this ring is real, but this is at the verge of 4 or 5 sigma detection, so we need more observed time to confirm this. This will mean that the inclination angle of the system will be 45 degrees, and it will mean that the mass of the Proxima B planet will be 1.8 solar masses. Okay? But this needs to be confirmed. So, in summary, what we found is that, well, here is the star. This is the planet discovered by Guillem Anglada and collaborators. There is some evidence that there is warm dust here, very close to the star, at 0.5 AUs or so. So there is also evidence that here there is something, a possible cloud of dust, or maybe not, maybe it's just noise. Then there is evidence that there is additional dust between 1 and 4 AUs, and there is evidence of an outer ring at about 30 AUs. What else can we know? Well, the uncertainties increase as we try to infer more information. We can tell about the temperature just using the Stephen Bowman law. The temperature decreases as the square root of the radius. So from the luminosity of the star, we can calculate the temperatures of these different objects. Also, we can calculate the mass of dust of each of these clouds. This is not very well known, but this is a lot of modeling about this, and a lot of uncertainties, because depending on the composition of the dust, the opacity change because of the different properties of the size distribution, but there is a lot of work made on that. Mayra has been modeling this for years. And using a typical opacity of 2 centimeters square per gram, we can calculate the mass of dust from the emission. However, here is something important to take into account. The grains of dust have different sizes, and they follow a power law with exponent of minus 3.5. So there is a lot of small grains, and there are a few big grains. So we are observing these rings. This is very relevant because the rings can be with objects of size 50 kilometers, for example. But ALMA is not able to see these big bodies. ALMA is seeing the smaller dust grains. So we have to extrapolate how many of the large bodies are depending on the emission that we have here. The mass is in these large bodies, but the emission is in these ones. So we have to take this into account. I did not pay too much attention to this law until a few weeks ago when I was removing the dishes from the dishwasher, and I break a plate. And I realized that the plate breaks very similarly to this, a very big piece, and then some intermediate, and thousands of very small grains that last in the kitchen for months, and you never. So ALMA is seeing these very small dust grains, but we have to infer which is the mass of the full plate. So we are using this law to extrapolate. Okay, so actually there are a lot of work on this, on how things break and how they go to this distribution of grain size. So if we play with these integrations, we can calculate the total mass will be the integrate from the minimum. This is the diameter of the dust grains, and this is the maximum diameter of the larger body. So it gives this result if we integrate assuming a constant density. So if we do the same exercise just for the dust, I will get this expression, very similar to this. So if I make the ratio between the total mass and the dust, I found that they are related in this way. So the total mass is equal to the mass of dust multiplied by the square root of the maximum diameter divided by the diameter of the larger dust grains that the ALMA is able to see, more or less. I can make some simplification because the minimum size actually is much smaller than the maximum, and then the final expression does not depend on all the parameters. So there is a lot of assumptions here. So I have to assume also which is the maximum size that the largest body I have. There are some calculations in the literature because with the age this size changes, but they are extremely uncertain. So I asked José Luis Ortiz and said, which is the maximum size that you find reasonable? Is it okay, 50 kilometers? So he said, okay, so we put 50 kilometers, but we left the result in terms of 50 kilometers because you can put your preferred size because there is a lot of uncertainty. And as a maximum size that ALMA can see, I put something of the order of 1 centimeter, and I assume that the minimum size of the dust grains is something of the order of 1 micron. Okay? But all of this is uncertain. So we obtain that the total mass is about 2,000 times the mass of dust that I calculate with this expression, which has a lot of uncertainties also. Okay? So using this, we obtain that this dust very close to the star, at 0.5 or so, will be at about 90 Kelvin of temperature and with a mass of 1,000th of the Earth's mass. This one, which we think is the analog of the Kuiper belt, will have a temperature of 40 K, which is similar to the temperature of the solar Kuiper belt, and a mass of 1/100th of the Earth's mass, which by chance is the same as the mass estimated for our solar Kuiper belt. But also in the solar system is extremely uncertain, this mass. Actually, I was looking at a reference just a few years older, and this value was 10 times bigger. So Jose Luis told me, no, do not use this, you have to. So I concluded that this was 10 times smaller than in the solar system, and finally, with the last estimate shown, they will be very similar, but this is extremely uncertain, just to have an idea. And the outer belt will be much more massive, about 1/3 of the Earth's mass, and very, very cold, just 10 K. So there is no way to explain easily how this can have been made. And also, we have this mysterious source, number 3. By the way, this is this nice plot, this nice figure was made by Manolo Lopez Puertas, working hardly with the help of Mayra. They were both playing with the colors and with the distributions of size, and they made this nice picture. Okay, so regarding this large source, we have many explanations. What this means that we have no idea. So the first possibility is that this can be just a peak of noise, and well, if we observe for a longer time with a longer integration, this will smooth and disappear. So we have to, this is just 2.5 hours of observation, so we cannot expect much more than it. However, if this was real, there are several possibilities. It could be a background galaxy. Actually, there is a population of background galaxies in this that I showed you before. This S1, S2, S3, these are thought to be submillimeter galaxies that appear in the submillimeter. And there are statistics of how many are of them do you expect per square degree or per square arcsecond. So the probability to find one of these background galaxies with this flux density at this distance, which is about 1.2 arcseconds from the source, is about 1/100. It's a low probability, but it's not extremely low. So I do not know. It can be, it can be not. Another possibility is that could be a superstellar object. It could not be a planet, because we calculated before that the planet would be much more weaker. But a superstellar object, a background, a brown dwarf, is possible. However, if you put a companion at a distance of 1.2 arcseconds, if this is a galaxy, the distance can be megaparsec. But this is a companion, then this corresponds to 1.6 astronomical units. So a brown dwarf at this distance will produce a shift in the velocity that will be detected in the observation. So I do not think this is a likely possibility. Another possibility is that this was part of a disk. So a disk seen edge-on, which was not completely symmetric. For example, this is the Beta Pictoris disk, which was one of the first disk around a different star, which is almost edge-on, and this side, for example, is brighter than this one. So if you see this with more noise, or it couldn't look, for example, like this. Well, this is a possibility. It cannot be discarded. Another possibility is that this corresponds to a collision of two planetary bodies or planetesimals that produce a lot of dust. The smashed sphere that we considered at the beginning, they can produce something like this. However, this is a 5 gigayears old star, so we do not expect that at present, in a star which is evolved as the sun, these kind of collisions are very frequent. So we think this is unlikely, but, well, we cannot discuss. Another possibility is that this was some kind of Trojan cloud. Actually, this is interesting because so far there is no any discovered analog of a Trojan cloud. And this will be an indirect way to detect a planet. We can see the cloud, we cannot see the Jupiter, but we can see the cloud. The problem is that we only have one, and the Trojan clouds are at the two Lagrange points, L4 and L5, and they are separated at angles of 60 degrees, so 120, so there is one missing. However, if the system is inclined, is not, here it's in phase on, then the part, like this part, actually it is observed, appears brighter than this one, because here there is more concentration of dust. So you have two Lagrangian points, and it happens that one of them is close to here, and the one is close to here in the other one, this will appear brighter, and with the sensitivity we have, it is possible that we only see it. So this is another possibility. Yeah, finally, the last possibility that I found extremely interesting, because we do not expect that, is that the mass of this dust, if you assume that it is contained in a planetary ring, so here the maximum size we put 10 meters, which is the maximum size of the bodies in the Saturn planetary ring, then you obtain a mass which is the same as the mass of the Saturn rings. So one possibility is that this is a planet. You cannot see the planet, but can see the rings. I found extremely interesting that ALMA has a sensitivity to detect the rings of a Saturn-like planet at the distance of Proxima Centauri. Anyway, any of these possibilities is very easy to check and discard. This with more sensitivity. The Proxima Centauri moves 4 Earth seconds per year in proper motion. Background galaxies do not move, so if we observe this after 1 year, Proxima Centauri will be very far from this position, so we can discard. This one is essentially discarded by the radial velocity observation. This one will see that this moves with the star. If we have this possibility, okay, then we will have that this will disappear. Will not be very convincing because it will be confused with just nice. This one, we will expect a motion, an orbital motion. It will move with the proper motion of the star, and then we'll have an orbital motion. At this distance, the period is about 6 years. So in 1 year, it moves 1/6 of the period. So it's a lot angle. By the way, be careful with the galley proofs in APJ because they put a 7 before this 5. I do not know why in the galley proofs. I did not check this, and now it appears like 80 years period. But with a 5 years period, this is very easy. And this one also is very easy because you will have the same orbital motion. So this is what we have learned. I think we now learn more than 1 year ago, but there is a lot of learn also for learning a lot. Thank you for your attention.
Okay, we'll have some time for questions. Who is starting?
If you say that this unknown source might be a Saturn-like ring that would be attached to a relatively large planet, right?
Yes,
so wouldn't that planet be visible in the radial velocities?
No. It will be. We considered that. It's a very interesting question. There is a relationship, empirical, more theoretical, between the mass of the planet and the mass of the rings. And we infer the mass of the planet from the mass of the rings. And it gives, as a result, a mass similar to the Saturn mass. And then we calculate how was the expected change in the radial velocity. And this at the limit of the sensitivity of the current observation. So in some additional time, when this the accuracy of the observations improves, it could be discarded, but it is just at the limit. And they found a small signal that can be, cannot be, but it's just at the limit. It's very, very interesting, your question. Of course, the proper motion will give additional information, because in a second epoch observation, if this is the planet, it will be like here or like here.
Is there any reason for the not coincidence between the center of gravity of your radio source and the optical counterpart, both in ACA and in full array observations?
This is within the uncertainties. The ACA observation is the one that has the poorer accuracy in the astrometry, and also the ACA observation, because of the lower sensitivity, the observation is spread over 2 months, and the proper motion of the source was more than 1 arc-second, and they were shifted every one. It apparently works well. Anyway, the beam is 6 arc-seconds, so it's and we cannot determine very accurately. But keep tuning, because we discovered something additional in the data, and perhaps we can refine this value a bit. And the other one, the position of the ALMA should be much more accurate than the optical position, and the accuracy of the optical position was about 0.1 arc-second, but this was within the uncertainty. So we cannot say that there is definitively something real in this. I was very surprised at the moment, because when we started the observation, Proxima Centauri was here. So we have to double check everything to be sure that this was the Proxima Centauri and this was another thing. But everything seems to fit.
Questions?
Guillem, do you plan to obtain observations at other wavelengths? Do you plan to obtain observations at other wavelengths?
Well, this is at the wavelength of 1.3 millimeters, which is band 6 of ALMA. We would like to observe at other wavelengths with ALMA, particularly at shorter wavelength. We would expect that the emission is stronger. It will be also interesting to obtain the spectral index in the millimeter range. Also, we have observed it at the centimeter wavelength that traces the non-thermal emission that could arise from instabilities in the surface of the star, magnetic activity in the surface of the star, or even to activity related between the star and the planet, in a similar way that happened with Io and Jupiter, and in a scale value. So we were observing at this wavelength looking for some kind of periodicities and things like this. And well, there are some results on this. And there are undergoing optical observations made by José Luis Ortiz, by the group here in the Department of Stellar System. And also there are undergoing infrared observations with Spitzer, and I think somebody has talked of other observation with Sophia or something like this. In the X-ray, no, in the radio there are these from centimeter to shorter wavelengths.
I just wanted to make a comment regarding observations with photometry, with photometric observatories. You may know that there have been already some claims in the literature of having detected a transit for Proxima b. There is a group, Chinese group, that has published very recently an event, a possible event for the detection of a transit of Proxima b from Antarctica, and there are some other attempts to well, or possible detections that have been published. Up to now, all these detections are not significant. They are not significant yet. They don't agree with each other, with the ephemeris of the planet orbiting the star. We have observations from Spitzer, which results I cannot advance yet, but hopefully soon we will provide some information on these runs with the Spitzer. But well, all of us know what the importance of knowing the inclination of the orbit of Proxima, you have Guillem has told us, is for the planet, because it gives us the absolute value of the mass of the planet, and then you can model the planet, the atmosphere, the internal structure with more accuracy. And in the system, you have mentioned, Guillem, that we get an inclination from the outer ring, but you didn't comment on the asymmetry that we see in the internal ring, and if the possible inclinations that can be measured from this internal ring coincides or agree with the external the inclination provided by the external ring, and of course these are different inclinations from 90 degrees that would allow a transit of Proxima b on front of its star. So there are some discrepancies there that still have to be concluded in some way.
This ring may be not real, so then just background sources that look like a ring. The other possibility is that it is real, but its inclination could be different than the orbital plane of the bodies orbiting in the inner part. So it is possible that this can be 45 degrees, and this can be edged on, and to here everything is plotted with the same inclination, but of course this elliptical orbit can be transiting, so cannot be discarded from this observation. From this ring number 2, we cannot derive the inclination. We only have an upper limit. We see that this object is elongated in this direction, which is pretty similar to the direction of the elongation of the outer ring, but we do not resolve the minor axis. So we cannot, we suspect that this should be elliptical, because if this axis was the same side as this one, we will also resolve this one. So we have some evidence that this is not completely phase on, inclination is not 90 degrees, but we cannot give a robust limit for the inclination in the inner size of the system. However, this is not a problem. We are far from the limits of both the sensitivity and the angular resolution of ALMA, so we can go closer to the star with future observations.
Okay. Let me finish just with the last question. I mean, having looked to this summary of results, number 5, I think is easy to check. Yes, integrating longer with ACA. And number 3, you have given us the different possibilities. Yes, you need a second epoch and see what has happened with this object. Number 4, what I think is a problem of sensitivity also, because in principle you will have the resolution to do it. It's a problem of integrating longer. Do you know how long should it be? I mean, hours with ALMA? Is it feasible?
Of the order of at least 10, 20 hours.
20 hours, okay.
One order of magnitude larger, because it depends of the actual size of this. If
yeah.
This is more compact with less time, but we do not know
That's clear, yeah.
The size.
And for number 2, do you have a configuration of ALMA that gives you the angular resolution necessary to discriminate this warm dust from the star itself, from the thermal emission? Okay.
We're made with an angular resolution of 0.6 arcsecond, and the maximum angular resolution ALMA can reach is of the order of 0.02 arcsecond. So it's more than one order of magnitude, and we can go very close to it. And because this is if this is compact, it is easier to detect, but in any case it's weak, because we are talking here of only 40 microjansky. We can do all of this in this star because it's the closest one. And what we are starting to suspect is we are seeing here some kind of phenomena that could be present in stars that are at longer distance and have not been identified so far. And we have found a couple of strange things that will be impossible to be noticed if the star was 5 times far away, for example. So the subtle changes of 40 microjanskis, it is extremely a small amount of emission that can mean very significant things.
Okay, then this is a target for ALMA cycle 5.
Clearly, okay. Don't feel bad because I don't know whether you have succeeded discriminating between Anglada Escudé and Anglada Pons, but in any case, you always be our Anglada. Okay, many thanks. Bye-bye.